Okay, here we have a tables that help engineer calculate phi factors. So the phi factor, which is a strength reduction factors, which makes the design safe against the factored load. So the phi factor, however, is directly related with the economies of the design. So we want to have the phi factor as big as possible unless it violates the design code. So the strength compatibility will serve to determine the phi factors based on ACI here. So we have a design regime for compression controlled, transitions, and tension controlled. So if you take a look at right there, this is what that is. I'm gonna erase some of them here. Okay. If you take a look at here, this is a compression control region, tension control regions, and this is a transition regions. The phi factor varies, changes depending on the regime or regions that we are designing for. For example, in compression control regions, we use a 0.65 for tidy columns and 0.70 for spiral columns, whereas the phi factor increases to 0.9 both of tidy columns and spiral columns when you are designing columns in tension controlled region here. So in all cases, again, the max compressive strain or maximum usable strain is limited to 0.003 compression. So this doesn't change at all. So that what we know here, your phi factor, strength reduction factor, increases as your ductility of the column increases. Okay, so that, and in transition regions, we're going to use a phi factor between 0.65 and 0.90, which is based on this formula. For example, tidy columns, we have a 0.48 plus 83 times epsilon t, whereas your spiral columns use this formula. And we have actually two formulas depending on 11 for A, 11 for B, and we have also two formulas for 11 5A, 11 5B for transition regions. Again here, maximum tensile strain at ultimate is higher or greater than 0.005 tension for tension controlled regions, or the tensile strain is between 0.003 and 0.002. Therefore, for transition regions, the tensile strain, maximum tensile strain you can get at ultimate is between 0.002 and 0.005. Okay, let's summarize phi factor depending on strength compatibility and the design reasons. Here again, if you are designing columns in compression controlled region right there, below this region. Okay, and when you're designing compression control regions here, you will use a phi factor for 65.65 and 0.70 for tied and spiral columns respectively. In this region, your tensile strain, epsilon t, is going to be between 0.002 tensile strain and the tensile strain corresponding to concrete strain of 0.003, which is compression. Okay, so this is how you're gonna take a look at the limit of compression control regions, and this, as you know, this represents a tensile or tension control regions where your reverse strain is greater than 0.005, where you are using 0.9 for both tied and spiral columns. And in between here, your phi factor increasing from this point to this point, and their interpolating equations are shown right there based on ACI 11 and 12, depending on A and B right there. So this is how you calculate phi factor for column design. And here, this is very important. Actually, this is not a ACI, this is ASC7, sorry about that. And you have another equation for ACI here. Okay, this is a ASC7 load factor sections. You will find them. And here, traditional ACI load factors can be found, and in between these two regions right there. Actually, the equations are a little bit different from they are similar. Okay, but still you can find these equations from ACI section 9.2, both ACI and ASCE as well, and you have a ACI load factors. So this is very important. So you have to use this table when you calculate phi factors for column design. So don't forget this. This is what happens. This is phi factor is multiplied to your nominal actual strengths and moment strengths, and they are greater than the factor load. And this is very important, so that this is sort of a ultimate design. You are calculating the nominal strengths where your compressive strength, concrete strength, corresponds to 0.003, and you multiply phi factor, which was obtained based on the previous table right there. Okay, and actual maximum actual load again is calculated this formula, and we determine this value to be 0.85 by the rectangular blocks, and we calculate the concrete area times the compressive rectangular equivalent block, and we have a rebar stress multiplied to rebar area, and we multiply phi factors right there. So phi factor is based on this table again. Okay, and we need to multiply 0.85 for spiral columns and 0.80 for tight columns. This is what we are talking here. See right there, the maximum usable actual load will be limited to 0.8 to 0.85 times the pure actual load capacity. This is just for a further safety. Okay, try to be further conservative when you're calculating actual force. Okay, so you can guarantee the safety factor, additional safety factor there. Now we are to calculate the strains based on the strain compatibility is here, and this is a rebars and columns. So now let's take a look at the column section. Here we are having a columns subject to the moment distractions here. So here we're going to have a compressions. Then I'm going to say that we have a neutral axis somewhere here, right? For example, this is just example. This is a neutral axis. Okay, this is a neutral axis. So this is neutral axis. Okay, this is a neutral axis, and we have a strain diagram based on strain compatibility. Strain compatibility. Compatibility. Okay, sorry about that. Compatibility. And we have a strains. This strain, we know the magnitude of this strain, which is 0.003, all the times, and we have a neutral axis, so that the strength at each layer of the rebars is proportional to the distance from the rebar to the neutral axis. So this is a compatibility concept, right? So this strain, magnitude of this strain at S2 layer is depending on the distance, this distance, which is from a rebar layer and the neutral axis. You can do same thing for the steel rebars, the first layers, third layers, and fourth layers. Now can you calculate, for example, the layer strength at this layer for rebars? Of course, this rebars is compressions. ESC, I would say. Okay, this is compression because they are in compression side. Okay, so how we're going to calculate this? Where we know the extreme maximum usable concrete strain is 0.003. Okay, this is quite a straightforward process, so that you have a triangular, similar triangular. Right, you have a similar triangle right there. For example, this triangle and this triangle are similar. Right, so that what you can do is establish equations. So this versus this is equal to this versus this. Right, this is the law, principle of similar triangle. So that we have 0.0033 versus, we have 0.003 versus C, and we have a compressive strain in third layers versus C minus D3. D3 is the distance from the layer of third layer of rebars from the neutral axis. This is a C minus D3. Alright, okay. So now from here we calculate easily C, which is the distance of a neutral axis, and then from which you can calculate the compressive strain in rebar, third layer of rebars, which is you see over there. Okay, and there you can calculate the other compressive strains of rebar consecutively, similarly. For S4, epsilon S4, you can substitute the appropriate distance from the rebar layers to the neutral axis, okay, which is governed by DC. Okay, anything else? It is straightforward, isn't it? Okay, this is possible because we know the 0.003. So this is fixed, so that, and this is fixed, and then we can find out these compressive strain of the rebars at each layers, which is very straightforward. And once we know this, we can calculate the force contributed by the structural components of the concrete block and each rebar layers, for example. And what is the compressive forces contributed by the compression block of the concrete? You just calculate 0.85 times F prime, see, we know that, and we calculate B, and V times A, right? So this beta 1 index can be calculated, depends on the compression strength of the compressive strength of concrete. So we know the A, you know the B, you know all numbers to calculate the force contributed by the concrete blocks in compression side. And also we have chance to calculate the force contributed by levers of each layer. So just nothing more than A times Fy. And Fy is epsilon times Young's modulus. Right? So if you are yielding with the levers, then we use a epsilon y is the epsilon I and E is limited by this value, Fy value. So we know that. Okay, so we all calculate these force components that involves with the column deformations, and we can establish the equilibrium equations. How can we do that? So let's take a look at here. Just simply the force equilibrium is very easy. Their net is equal to the force which is acting on the column. Okay, now we can establish equilibrium equations by adding compression force from concrete and the compression force from levers, from which you calculate right there. See, so this concrete component and lever component is gonna produce a axial force, nominal axial load capacity. This is how you calculate nominal axial load capacity, as long as you have a compression force due to the concrete and compression force due to the levers. Okay, and the moment is very easy too. Now we can calculate moment equilibrium using this equation, but this equation we have to fix one thing here. This is a I, not 1. This is I. Okay, so this equation gives you the moment equilibrium. For example, the moment contribution due to compression block is multiply Cc by this is moment arm, h/2 minus a/2. If you take a look at here, let me erase something here. Okay, this is your compression block. Say somewhere here, this is Cc, and your moment contribution due to this is to multiply the half of the sections, which is h/2 minus half of this A, so that minus a/2. So you can calculate this way right here. Okay, so this little math gives you the moment due to compression block. And what about the moment due to levers at each layer? That's easy too. If you take a look at right there, let's take a look at this one. Is easier to understand. Here, for example, F4 is multiply the moment arm, which is this. Right? This is just nothing more than subtract this from h/2, and this is d4 by definitions. If you go here, this is d4 for fourth layer, d3 for third layer, d2 for second layer, d1 for first layer. Very systematic, isn't it? And you multiply, so fs4 to d4 will give you a moment contributed by the fs4. Similarly, you can do this fs3 is multiplied by the distance here, which is calculate subtract h/2 minus again D3, and here this we change the directions. Fs2 multiply the distance, which is this, okay, and this is a minus h over 2 minus d2. Okay, so this is h over 2, see, h over 2 minus d2. So this changes direction because you are under the neutral axis. This moment contribution due to the Fs2, the lever of second layer, is nothing more than this distance times the Fs2. Then this distance is calculated h over 2 minus d2 and minus of it, right? Okay, this, you got this is negative value, and this also you have a clockwise, whereas you have counterclockwise, so you have another minus over there. So this is also should be added into your equilibrium equations right there, right here. So you end up with a entire moment equilibrium equations based on compressive block and the levers of all layers. Don't forget that if you take a moment with respect to the neutral axis right there, neutral axis right there at this point, and this is a counterclockwise, this is a clockwise, so you have to put the minus up there, and this value is minus originally. Okay, so these equations is another straightforward relationships that you can calculate your moment equilibriums based on compressive blocks and the levers of all layers. And this is your nominal moment capacity, and this will become your nominal axial load capacity. So this is Pn and this is Mn. So you can simply calculate it. And all calculation, you have to assume that your compressive concrete is 0.003 right there. Okay, so do you follow me? Okay, let me just go through one more time quickly to help you understand. Okay, now we're gonna start take a look at the strain compatibility formulations of the concrete block and levers. Here we have 4 layers of levers, can be easily calculated as long as you know the epsilon cu, which is maximum usable concrete strain, is assumed to be 0.003 at here using a similar triangle and these equations. Take a look at this equation few seconds. See, this versus this is equal to this versus this, or this versus this, or this versus this, whatever. So you can calculate the neutral axis, and from it you also calculate all strains at all layers of levers depending on your distance, D1 to D4, for all layers. So this step is very straightforward from here to here. Okay, now we calculate all strains of levers as long as we know the concrete strains, which is 0.003. Okay, anything else that you want to ask me questions, and take a look at for a second, and if you're not sure about it, then repeat this video. But this is very important. This will provide you the base for calculating the interaction diagrams and you're going to probably practice yourself using Excel, but the establish equations in Excel is very straightforward if you understand these concepts, right? All you need to do is just fit in the cell with the formula, right? Okay, now we're ready to calculate the nominal values of P and M right there. Okay, P and M right there. So P and M is also very straightforward because you know that the P equilibriums is just simply obtained by adding compressed block that you calculate here. You calculate here, right? This is you have somewhere CC here, and this is each compressive forces due to the rebarriers. Okay, you just add them up. That's it. And when you add them up, when you calculate the force in term, you have to understand this. But this also dealt with LC1, I think. Take a look at that. See, your stress can be calculated this, right? This is Young's modulus. But when you are talking the reason where yield, you take Fi value. Okay, this is only one thing that you have to be careful. Otherwise, you use this formula. But if your strengths go there, right there, epsilon, you don't take this value. You don't take this value. Do you understand? You don't take this value. You have to take this value. Okay, because this is yielding. There's no increase of stresses after yielding. So this is what happened, right? And also when you calculate, this is very important. When you calculate the stresses or force by the rebars, and you have to subtract the concrete from rebar stress.